Resuming our story, when last we talked, I told you that sciences begin around a problem, some problem that's very important to people, that takes a long time to solve, and yet a problem that's not impossible to solve. And astronomy began around the problem of telling the future. You see, people always want to know what's going to happen tomorrow, next week, next month, next year. And it was believed for a long time that the planets controlled the future. So if you could tell where the planets would be in the future, you'd be able to tell where you would be in the future. And people spent a lot of time and effort trying to find means of predicting the future positions of the planets in the sky. Chemistry began because people wanted to find a way to make gold. Now the idea to make gold was that there was something corrupt in lead. Lead was corrupted, iron was corrupted, tin was corrupted because all these metals rust and rot. But if you could take the corruption out of lead, what you'd be left with would be the pure essence, which was gold, which doesn't rust. And so the people spent a lot of trouble doing that, and that was the beginning of chemistry. Of course, not only if you could take the corruption out of lead, you'd have gold. If you could take the corruption out of people, they would never get sick and they'd live forever. So it had, not only would you be able to make gold, you'd be able to make medicine. And that was the problem that got chemistry started. The problem that got physics started was the problem to make a machine that would run without effort. It was noticed, people saw that you could make machines, and the smarter you were, the better you could make a machine that would do more things with less effort. And it was supposed that perhaps you could make a machine that would run by itself forever, once started, or maybe it would even start itself. And of course that machine has a name, a perpetual motion machine. And the essence of that machine was that maybe you put in a little bit of effort or work, but it puts out in return much more effort, much more work. And you say, well, of course that's great, but why would people believe in such a thing? And again, remember, these people we're talking about are not people think that in the olden days people were dumb. Actually, I think nowadays people are dumb. In the olden days people were smart. Those Greeks that thought about these things in 2,000, 3,000 years ago were very, very smart people. So you have to ask, why did they suppose that there could be such a machine that you could put a little bit of work into and get a lot of work out? And the reason that they thought that was that these people were familiar with the lever. Now the lever is a machine like this. It's a lever is the same thing as a seesaw. And if you put the pivot in the middle and you put a certain amount of force in here, pushing down, this end will come up and a certain amount of force will come out of this end. But you can pull a little trick with this thing, and if you put the pivot over here at this end, then you can put a little bit of force here, but what will come out of here will be a whole lot of force. You'll get a lot of force coming out of this end. And so they said, well, look, if you can get more force out of that end, then perhaps we can make a device that will put more work out. In other words, there are cases in physics where you can put in a little bit of something and come out with more. Okay, so that was their thought. Now, to proceed with this, we have to talk about what is work. That's the way we make progress. What is work? Now, and for the time being, I'm going to say that work is the same thing as energy. It'll turn out much later, you'll see that work is not always the same thing as energy. But that was a discovery that was to be, 100, maybe it was 200 years in the future. At this time, people thought work was the same as energy, and in our talk, we're going to assume that work is the same as energy for the time being. So there comes a question, what exactly is work? Now, some people will say, I'm doing homework. But of course, if you look at the person who's doing homework, often a person who is doing homework is in bed reading a book, and they say they're doing their homework. And kind of wonder, how can a person be doing work if they're in bed? Other times people will be doing their homework, particularly if they're doing math homework, they'll be sitting at a desk, but they're still sitting with their butt in a chair. So how can they be doing work if they are sitting down? I love when I have to call up somebody at a bank or something like that and they give me a hard time. I love to say, and they say, well, they tell me they're busy working right now. They're busy working. I say, you're busy working. Are you sitting down? They say, yes, I'm sitting down. I say, how can you be working if you're sitting down? You tell that to a bureaucrat sometime on the telephone. You'll have a lot of fun. You'll see how mad they'll get. But what we have to do, we have to find an example of something that everybody will agree on is work. We have to, and this is how things are done in physics. You find something that everybody will agree is work, and then from there on, then you show other things are like that. So first we have to agree on one thing that is work. And I think we can all agree on one thing that's work. If you're actually out in the yard and you have a shovel and you're digging and lifting up stuff, and you're digging and the hole's getting pretty deep and you're lifting up stuff, you're doing work. That's something everybody will agree on is work. Now, the next thing is let's think a little bit more. Let's think a little bit more about work. One example of work that everybody will agree on is picking something up. So let's pick something up and have just one example of work that we all agree on. Here is something, and let's say this thing weighs a pound. 1 lb. 1 pound. And now I'm going to take this thing and I'm going to lift it up a certain distance, let's pretend a foot. And I lift it up to here, I do a certain amount of work. A certain amount of work. Okay, it's up there now. So, lifted it. Okay. Now, I want to ask another question. We're beginning to think about how you think about work. Now let's suppose we have something else, and this is not 1 pound. Let's suppose this object that we have next to lift is 2 pounds. More stuff inside the box. And I take this 2 pounds and I lift it up the same distance. So now it's up here. The 2 pounds is up here. I've lifted it. It's not down here anymore. Question, have I done more work by lifting 2 pounds than 1 pound? Of course, having done a little work yourself and having lifted things, you know from experience that you've done more work. Now the next question is, how much more work have you done? You say, well, right away, twice as much. Why? Why twice as much? Well, first it was 1 pound, then it was 2 pounds. Okay, it turns out you're right. Lifting 2 pounds is twice as much work as lifting 1 pound, but the reason, just saying because it's the number 2, it's twice as much, that's okay for a first guess. In fact, that's the right first guess to make. It's the correct guess, but it's just a guess. Because I'm going to tell you about some situations in physics, not now, but later on, where when you double something, the effect does not double. I'll tell you something that we're going to come to later on in these talks. If you make a bullet go at a certain speed and it hits the wall, it'll make a hole a certain distance into the wall. If you were to make that bullet go twice as fast, you'd say, well, how much deeper would it go? Would it go deeper? Of course it would go deeper. Then how much deeper? You say, well, it'll go twice as deep. Wrong. If you make a bullet go twice as fast, it goes 4 times as deep into the wall. So you can't be sure just because you double something that the effect is going to be doubled. But of course, in this case, it is doubled. Now, why is it doubled? Why when you lift a 2 pound weight do you do twice as much work as lifting a 1 pound weight? I'm going to tell you a basic principle, that it's a simple principle, but its simplicity should not hide its importance. Just because you see something that's simple, you think, oh, well, there's nothing to it. But this is a very useful principle. If you look up the definition of 2 in a dictionary, Webster's dictionary, do you know what the dictionary definition of 2 is? The dictionary definition, what is it? The dictionary definition of 2 is 1 plus 1. Incidentally, the dictionary definition of 3 is 2 plus 1, and on like that. But using that idea, it's very useful, because what is a 2 pound weight? A 2 pound weight is really 2 1 pound weights glued together. And that's the idea. Now let's go back. Why is it twice as much work to lift 2 pounds? I will show you why it is. Because this 2 pound weight that I have here is equal to 2 1 pound weights. make them try to look about equal. Okay, now, if it's two 1-pound weights, we know how much work it is to lift a 1-pound weight. We already did that, so we can just lift the first 1-pound weight and it's up here. And then I can just lift the second 1-pound weight. And you can see, well, look, I've done the process twice, so whatever work it was to lift the 1-pound weight, to lift the 2-pound weight, it must be twice as much, because 2 pounds is really two 1-pound weights glued together. So it is twice as much weight to lift 2 pounds. Okay, so much for that. So now we're beginning to of course, maybe we're making a big deal out of a little thing, but we're not. We're not making a big deal out of a little thing. Now I want to ask you another question. Here's the next question I'm going to ask you. Let's go back to the 1-pound weight again. And here is a 1-pound weight. There's a 1-pound weight. Now, if I lift it up here, up 1 foot, lift it up 1 foot, I do a certain amount of work. By the way, it's getting to be too much trouble for me to write pounds, and since I'm always talking about pounds, I'm just going to put a 1 down here. That has another advantage too, because things aren't supposed to be made in pounds anymore, isn't that right? Now things are supposed to be kilograms. Heaven knows what they're supposed to be next year. So that way, if it's 1, it can be anything. Anything you want. 1 ton, 1 ounce. So I lift it. So I do a certain amount of work to lift this thing 1 foot. Now, the question I want to ask you is, suppose instead of lifting it 1 foot, suppose I lift it 2 feet. In other words, instead of lifting it over to here, I lift it all the way up to here. Put the 1-pound weight up here. See, I don't lift it up there. I lift it up 2 feet. I lift it up twice as high. How much more work have I done? Well, again, you might say, well, how much more? Look, before you lift it 1 foot, now you lift it 2 feet, so you do twice as much work. But how do you really know? Because before I lifted it up to here. Maybe my arms, maybe something happens with your arms when you lift something up to here. Something changes. Something changes, so that the second part is different than the first part. So how do you know that it's really twice as much work? Again, you can use the same idea that we used before. You can say, hey, look, don't lift it all the way up there. Don't stretch your arms that much. Bring it down to the ground, floor, and first of all, lift it up to here. Like that. Okay. Then, after you get it up to there, you can go up and get yourself in the same position like you were before. So now you can be here, and now you can lift it up to here. Only you don't have to reach so high. You just use the same motion that you used before. You can repeat the exact process that you used before. And now you lift it up to here. And now you can see that we got it up to there by doing twice what we did here. We went from here to here, and then we repeated the process again up to there. Now you have to be very careful that we really did repeat the same process the second time. And for this reason, you mustn't suppose that if we keep lifting the object higher 1 foot more, 1 foot more, 1 foot more, it'll always work the same. And would it work the same? No, it won't work the same, because as you get higher and higher on the earth, you get further from the earth, and the gravity gets less and less and less. Gravity gets very weak when you get quite high. So you have to show that the work to lift it, or not the work, but the circumstances in the second lift are exactly the same as they were in the first lift. And of course, if you got very high, they certainly wouldn't be the same anymore, because you'd be very far from the earth. But down close to the surface of the earth, gravity, while it gets weaker as you go up higher, it doesn't get noticeably weaker, and so we say it's the same up there as it is down here. Okay, so to summarize. Well, I won't summarize. I'm going to ask you a question. Which is more work? Which is more work? You can lift 1 pound. You can lift it up 2 feet. Or you can do this. You can take 2 pounds, and this time I'll draw make the object bigger say we'll call this at 2 pounds, and lift it 1 foot. There. There. I will call this 1 foot. Make it look neat. Put a 1 in there so you know it's up 1 foot. Okay, now the question is, which is more work? To lift 1 pound 2 feet or to lift 2 pounds 1 foot? Well, we've already discussed this. We know that both of these things represent twice as much work as to lift 1 pound 1 foot. And here is a picture of lifting 1 pound 1 foot. Okay, 1 pound 1 foot. This is twice as much as that, and this is twice as much as that. So we know that these two things are the same. It doesn't really make any difference. The work of lifting 2 pounds 1 foot is the same as the work of lifting 1 pound 2 feet. All you take is you take the number of pounds and the number of feet that you lift it, and you multiply the two together. And if that comes out the same, then the work is the same. And now we're beginning to see what work is. We're getting an insight. Work does not depend upon the force alone. Work is not force. Well, force is the weight. Force is a fancy word. A pound is a certain amount of force. But it doesn't depend upon the weight of the thing or the force of the thing. It depends upon the weight of the thing multiplied by the distance that you lift it. And so you can have all different forces, 1 pound, 2 pounds, and you can still make them do the same amount of work if you lift them different distances. The 2 pounds you have to lift only half as much as the 1 pound, but the work will come out to be the same. And since it's the work depends upon the weight multiplied by the distance that you lifted, or the force multiplied by the distance that you lifted, they say that work is measured in foot-pounds, the number of feet times the number of pounds that it's lifted. And foot-pounds is the natural measure for work. You know, there's a natural measure for various things. The natural measure for time is hours. The natural measure for cheese, I guess, if you're buying cheese, the natural measure for cheese is how many pounds it takes. If you're buying some liquid like wine, you buy it by the gallon. My father used to buy wine by the gallon. People now buy it in these little tiny bottles, but in the days when I was a kid, they bought it by the gallon. The natural measure for gallon is for wine is a gallon. Natural measure for yarn is the foot, or wire or cable is all sold by the foot. Real estate is sold not by the foot, but by the square foot. Isn't that right? And so you say, well, various things are measured in various ways, and what is the way that we should measure work? What are the natural units of work? And the natural units of work are foot-pounds. That's the number of feet that you lift the thing multiplied by the number of pounds that you lift it. Now, of course, it doesn't have to be foot-pounds. It's just like the natural measure for money has to be dollars, but the natural measure for money doesn't have to be dollars. It can be yen, or it can be Deutschmarks, or it can be pounds, or it can be shillings, or it can be zuzem. There's all kinds of different ways that you can measure money. And so it is, you don't always have to measure work in foot-pounds. You have to take some unit of distance, like say a meter, and some unit of force, like say a Newton. A Newton meter is another measure of work. Or it could be an ounce, inch, 1 ounce, a force of 1 ounce pushing for 1 inch. Or it could be a dyne. A dyne is a fancy unit, a little tiny unit of force in the metric system, pushing for a centimeter. A dyne centimeter is a unit of work. Of course, a dyne centimeter is going to be very small compared to a foot-pound. It's like a penny compared to a dollar. But nonetheless, you can measure your money in pennies. Now, you might have heard of other units of work, too. Sometimes energy or work, when you buy it from the utility company, you buy work in kilowatt hours. It turns out you can look into a physics book and you can see how many kilowatt hours make a make a foot-pound. It's all convertible. Other units of work, let's see, there's a foot-pound, a kilowatt-hour. Other units of work are joules, or a horsepower hour is another unit of work that converts into foot-pounds. And British thermal units, that's another unit of work, and that will also convert into foot-pounds. All of these things will convert into foot-pounds. But to do work, you have to make a certain weight move a certain distance. Well, now, after analyzing this, when you learn something in physics, if it's going to be useful, it should help us understand a problem. And let's go back now to that problem that the Greeks worried about, which is the lever. And why back to the lever? Because it was the Greeks' hope that the lever might somehow be a key to a machine that would put out more work than it took in. In other words, there was some thought in ancient times that perhaps something like a lever would allow you to put in a little bit of work and get out a lot of work. And now that we really know what work is, let's go back and look at the lever and see if there is some possibility that the lever will put out more work than it takes in. So I'm going to draw a big lever on the blackboard. And here we go. I'm going to draw a big one because we have to analyze it in some detail. And that's why we need it big. Now, let's see, let me draw a lever like this. And actually, I'm going to draw a lever that on this side is, let's say, 1 unit long on this side. And on the other side of the lever, it's going to be 1, 2, 3. This is called a 3-to-1 lever because it pivots here, and the left-hand side is 3 times long as the right-hand side. And if I put a certain amount of force here, I'm going to get out some force. Remember, this thing's going to twist. I'm going to get out some force coming up on this side. And I think everybody knows how much more force I'm going to get on that side with a 3-to-1 lever. I'm going to get 3 times as much force coming up on this side here as I put in. So the force is multiplied by 3. There's no doubt about that. But now let's talk a little bit about the lever action. Let's suppose that this side goes down an inch. I actually push it down, and it goes down an inch. And we say this side goes down. How far does it go down? 1 inch. Now this side on the right, it's going to go up. Is it going to go up as much as the other side goes down? Well, let's see. No, it doesn't go down. It goes up. What am I talking about? It doesn't go down at all. It goes up. But does it go up as much as this side goes down? It goes up less. How much less? Well, let's think of this as a scissors. Here's the original position of the lever, like so, and there's the pivot point. Let's trim it up so that it looks the same on both sides. And there's a line. And then the line pivots, and this side comes down a little bit, and this side goes up. And of course, this makes isn't this a little triangle on this side? You know, where this went down a bit, and this side goes up. Here we have 2 triangles. And the triangles are really, in a way, they're the same. They're like this triangle is essentially a miniature of this triangle. And you say, why is it the same? Well, this angle here, this angle is the same as this angle here, isn't that right? And these 2 sides of the scissors are the same as these. In other words, this side of the scissors equals this side. Whatever the length is here, it has to be here. And this length equals this length. So they're triangles that have 2 sides which are the same, which I think has the fancy name isosceles triangles. That's a Greek way of saying 2 sides are the same. So these triangles are the same. And this triangle here, the point I'm trying to make is this triangle here is just a miniature of this triangle. This is a big version of that little triangle. And always when you make a miniature, you say, well, this is a half-scale locomotive, or this is a 3rd scale ship, model ship. This model is actually, what is the ratio? It's actually, we agreed up here that this is a certain distance, and this is 3 times as long. It's a 3 times lever, so this is the ratio of this side here to the long side here. This triangle is 1/3. Everything here is 1/3 of here. If this is 1 inch, then we know what this has to be. This has to be 1/3 1/3 of an inch. So when the big side goes down, little side goes up, just 1/3 as much. Okay. Now remember our problem. Our problem is to see if we can get out more work. To see if we can get out more work. But we know what work is. We know what work is. Work is force times distance. Knowing that, how much work goes into this side? Well, let's say, what does this represent? Well, I'd say it's 1. 1 what? Well, let's say the force here is 1 pound. And how far does it push the lever down? Well, we could say it's also 1. 1 what? Well, let's say 1 foot. Or what was it, 1 inch? What did we say before? Well, it doesn't matter what. We'll say it pushes it down 1 foot. So it pushes it down 1 foot. So how much work goes into this side of the lever? 1 foot-pound of work goes in. Now let's go to this side of the lever over here and see how much work comes out. Again, we have to take the force. What is the force over here? Well, you can see the force is 3 pounds. So what comes out of this side is not 1 pound, but 3 pounds. But what's the distance that it moves it? How many feet? We know that. It's 1/3 of a foot. 1/3 of a foot. If you take 3 pounds and multiply it by 1/3, what do you get? What is 3 times 1/3? Or what is 1/3 of 3? 1/3 of 3 is 1. So on both sides, 1 foot-pound goes in and 1 foot-pound comes out. The lever does not put out more work than goes in. The lever puts out exactly as much work as goes in. What does the lever do? The lever is in a way a transformer. You see, it turns out that work is force times distance. And you can get more force if you get less distance. Or if you get more distance, you can get less force. And the lever is just a transformer. It takes advantage of that, but it does not give you more work. It can give you more force or it can give you less force. It can give you more distance or it can give you less distance. But every time it gives you more motion, it gives you less force. And every time it gives you less motion, it gives you more force, but the product of the two stay the same. The product of the two stay the same. It's a little bit like economy. People always want more money. And so the government passes laws every so often that the minimum wage is increased. And then everybody gets more money. But it turns out that the money buys less, produces inflation, so everybody stays the same anyway. It's the same with this. You can get more force, but you get less distance, and the work is the product of the two. Okay. Now, I want to point out two kind of deep points. It's interesting that to analyze how the lever worked, this analysis of the lever working, we imagined that the lever moved a little bit. We imagined that the lever moved. That was how we analyzed it. But in reality, very often you have a lever, and supposing the lever did not move at all, suppose it was just stationary. Just stationary like this. And on this end, we put a 3-pound weight, and on this end we put a 1-pound weight, and they just balance. It doesn't move at all. The lever works when it stands perfectly still, and yet to analyze it, you have to imagine that it moves a tiny bit. That's a strange thing about physics. Sometimes in physics, to explain why the world is the way it is, you have to kind of imagine what would happen if it were in a different way. And in imagining the world in a different way, you're able to tell about how it works the way it is. That's something that's worth thinking about. We might come back and talk about that a little bit more. Okay. And that idea will turn up again and again in physics. I want to talk about something else now. I want to ask a question. Now that we know what work is, I want to ask a fairly important question. There's a fellow called Charles Atlas, and he holds up the world. I'll be Charles Atlas. And here's the world. And Charles Atlas holds up the world perpetually, day after day after day, or at least all day long. Now, I want to ask you a question. When Charles Atlas holds up the world, is he doing any work? Well, there's two ways to think about it. One, does Charles Atlas get tired? If you spend the day holding up the world, would you get tired? I think the answer is yes. So you'd say, well, maybe Charles Atlas is doing work. But of course, then you could always say, well, how much work is Charles Atlas doing? Well, he's putting out one hell of a lot of force. He's holding up the whole world. But force alone is not the measure of work. You have to think of distance. How high does he lift the world? Does he move the world? Well, it turns out that all day long he doesn't move the world an inch. He just keeps it where it is. Now, granted, if Charles Atlas was lifting the world up, then he'd be doing work. But if he just stands there, how could he be doing work? You might be able to just put a fancy post underneath the world, and that post could hold the world up. See, and it would be an inanimate object. You can't say, is the post doing work? So it's a paradox. It's a paradox. Is Charles Atlas doing work as he holds up the world? He's certainly getting tired, but is he doing work on the world? Or is he doing work? I should phrase it that way. And the answer is yes, Charles Atlas is doing work, because he gets tired. But is he doing work on the world? And the answer to that question, is he doing work on the world, is no. Charles Atlas is doing work, but he's not doing work on the world, because if he were doing work on the world, then the world would be higher. In fact, what he can do is he can take all the energy out of the world in the morning by dropping the world and hearing it go bang. And then he could lift it all day long, keep it at the same height, and then drop it in the afternoon. Would it make a bigger noise in the afternoon or in the morning? The noise would be the same, which goes to show that he hasn't really done any work on the world, because when all the work comes out and makes a bang, it's the same. But the point is, Charles Atlas is doing work. What's he doing work on? What is Charles Atlas doing work on? Well, that's kind of hard to tell. So again, we're going to use a favorite trick of thinking about physics. And that is, when you can't answer a question, you ask another question about something else. Generally, if you take exam-taking strategies, one of the things that people learn in school is strategies for taking examinations, and they tell you not to think about other questions. You should think about the question you're asked and not think about other questions. That's a strategy for taking examinations, perhaps. But in thinking about physics, if you're a serious physicist, that's exactly the strategy you use. If you can't answer a question, you do think about another question. It's exactly the opposite of exam taking. Perhaps that's why exams are such poor measures of who will do well in physics once school is over. But at any rate, let's ask another question, and let's take a helicopter. And here's a I don't have to draw it. Here's a helicopter. Bop, 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 bop. And the helicopter isn't going up or going down. The helicopter is just hovering, and the blades are going around like this. Is the helicopter doing work? Well, it sure as heck is doing work. It's using up all the gasoline inside of it. But is the helicopter, what's it doing work on? Is it lifting anything? No, the helicopter spends an hour hovering in one place. It's not going up or down. So where's all the work going? The work is going into the air and into heat. What it happens is that it's thrashing the air, and as the motor runs, it's heating the air. It's not, the work is not going into lifting anything. It's not going into the helicopter. The work in this case is going into the air itself. That's what the helicopter is working on as it beats its blades and pours heat out of its engine. And it's the same with Charles Atlas. When Charles Atlas is holding up the world, Charles Atlas is not doing any work on the world because he's not lifting it. He's just holding it in one place. If he moved it 1 inch up, then he'd be doing some work on the world. But he's not. He's just holding it in place. So he's not doing work on the world. But he is doing work. He's getting hot. He's perspiring. His metabolism is running. Charles Atlas is doing work on the same thing that the helicopter was doing work on. He's doing work on the air, because if he stands there holding up the world, the air will be hotter by the fact that he's holding it up. If Charles Atlas spent the day in the same room, not holding up the world, the air in the room would be a little cooler. But if he has to spend the day holding up the world, the air in the room is a little hotter because Charles Atlas sweats more, and that's where the work goes. Okay, good enough. Well, now I would like to give some examples of some other things to show you how we can use some of these principles that I've talked about. Understanding what work is a powerful key to understanding a lot about the world. And I'm going to show you some things about the principle of work. In fact, I'm going to show you some things about levers. Now, the key thing to understand, thinking about levers in terms of work, is that a lever is a thing where one end moves a lot and the other end moves a little bit. Keep dropping my eraser. But here's a lever, and a lever, to review, is a device. Now I'm drawing it very simple. It's just a stick like this. But there is one end of the lever. When you wiggle the lever, one end moves a lot and one end moves a little bit. This is the end that moves a lot, and this is the end that moves a little. This end moves a little, that end moves a lot. And it turns out that when you have a situation where one end moves a lot and one end moves a little, that the forces at those two ends are not the same. The big force is always at the end that moves a little, and the big force is at the end that moves a little, and the small force is at the end that moves a lot. And it turns out, of course, that not only is that the case, but that the ratio is the same. In other words, if this end moves 10 times as much as this end, if the ratio of the motions is 10 to 1, then the ratio of the forces at the two ends is always 10 to 1. And which end gets the big force? The end that moves the little gets the big force, and the end that moves the lot gets the small force. It's as if God were compensating somehow for the fact that one end moved a little, and the compensation is that it gets the big force. Now, levers are not the only things in the world. There are many things in the world, and they used to be called machines. And a machine was always a device that was so contrived, that one end of the machine would move a lot and other end of the machine would move a little. And when that would happen, the forces at the two ends would be different. And I'm now going to show you a whole bunch of machines, which in one way you could call disguised levers, where one end moves a lot and the other end moves a little. Well, let me begin to show you some of these machines, some of these situations. And this is the first one that I'm going to show you. Now I'm going to show you something surprising about levers. On top, I have a whole bunch of little levers, all in a row. And each little lever, you can see on the right side it has a certain length, and on the left side it has twice as much length. On the right side a certain length, twice as much on the left, a certain amount on the right, always twice as much on the left as on the right. And I'm going to hook these levers together to make a contraption out of it. This is a straightforward contraption, what they used to call in the olden days a Rube Goldberg machine. There was a cartoonist by that name who drew strange contraptions. And to turn this into a Rube Goldberg, I'm going to take this end, and I'm going to put a chain link through there. So that when you push this end down, this end goes up, of course, but since it's chain linked, the other lever is going to be drawn up exactly the same amount. It has a ring through its tail there. And when this end goes up, of course, this end of the lever over here is going to have to go down. But if this end goes down, I'm going to put a chain here. And since the chain link there, it's going to make this end go down over here. If this end of this lever goes down, the other end is going to go up. And if I put a chain link, it's going to make that lever go up too. And now the story repeats. This end goes down. A chain link through here causes this end of this lever to go down. If this end goes down, that goes up. As I said before, a Rube Goldberg machine. Now, that's pretty much of a kludgy mess. So instead of that, on the bottom I have a simpler version. It's just one long lever. This long lever on the left-hand side, it's just as long as all these levers put together were up here, up to the last pivot point here. And down here on the right-hand side, there's just 1 unit length on the right-hand side, and there's 1 unit length on the right-hand side. These levers are the same to the right, and they're also the same to the left, except the bottom one is just one clean, simple lever, and the top is a complicated compound machine, all one part sticking to other parts. Now let's analyze them. Well, to analyze them, let's start with the bottom one first. Let's start with the bottom one first. And let's suppose that on the bottom one, I put in 1 pound of force here. This end goes down. This other side goes up. How much force comes out of the other side? Well, right away you can count how many. Well, this is 1 over here. How long is this? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This side lever, this is 14. This is 1. This is 1. This is 14. The bottom lever is a 14-to-1 lever. So sure, a force is going to come out of the right side. How much strength is it going to have? 14 times as much as the strength. So 1 ton goes into there, 14 tons come out of there. If 1 pound goes into there, 14 pounds comes out of there. If 1 kilogram goes into here, 14 kilograms come out of here. Now, before we finish with the bottom one, let's ask one more question. Supposing I push this end down 1 inch. So this end actually goes down 1 inch. That other end is going to come up. How far up is it going to come? 1/14 of an inch. You can see that because the ratio is 14-to-1, isn't that right? To 2 lengths. And it has to be 1/14 of an inch because that also makes it conserve work, because the amount of work that will come out of here, 1/14 of an inch multiplied by 14 is the same as 1 times 1 over here. Okay, so this lever magnifies the force 14 times. Now let's analyze the lever, the top lever. How does it work? Well, it's not a 14-to-1 lever. This is a lever that has a certain length on the right-hand side of the pivot, and a certain length on the left-hand side. And on the left-hand side, there's twice as much as on the right-hand side. So if you start with putting 1 pound into here, how many pounds will come out of the right-hand side? 2 pounds. Now, how many pounds get put into the second lever? Well, there's a chain link there, so you get 2 pounds into the second lever. Now, what does the second lever do? Well, it's a 2-to-1 lever, which means that whatever comes into the left-hand side, twice as much comes out of the right-hand side. It multiplies whatever force goes into it by 2. And so what's going to come out of the right-hand side is 4 pounds, 2 times 2. So what goes into the third lever here? 4 pounds of force. What does this third lever do? It also is a 2-to-1 lever, so it's going to throw out twice as much as comes into it. What comes into it? 4 pounds. So what comes out of it? Twice as much. 8 pounds. You're going to get 8 pounds out for 4 pounds in. Next, we come to this next lever. What goes into the next one? 8 pounds go into it. What comes out? Twice as much. What's twice as much as 8? 16 pounds come out of this lever. 16 pounds. What goes into the last lever? 16 pounds. What kind of a lever is the last lever? The last lever is a 2-to-1 lever, like all the other levers on top. It multiplies whatever comes into it by 2. What's 2 times 16? 32. So the top lever is different than the bottom lever. It's true they're both just as long, and the space on the right-hand side of them is both the same. But this one, you put in 1 pound, you get out 14. The top one, you put in 1 pound, and you get out 32, a lot more. a lot more. The top lever is what's called a compound lever. By the way, before we go on to saying a few words about compound levers, let me ask another question. Let's suppose the end of this lever wiggles an inch. Of course, this end's going to wiggle too over here. How much is this end going to wiggle over here? There's two ways to think about that. There's two ways to think. One way, we can just think in terms of energy. We know the energy that comes out has to be the same as the energy that goes in, otherwise we'd have a perpetual motion machine. So if the energy that goes in is 1 pound, pushes 1 inch, it's 1 inch pound. This is 32 pounds that come out here, but it still has to be 1 inch pound of work. So how far does it move over here? Well, we say it can't move an inch. It can only move 1/32nd part of an inch. So this thing, if this end wiggles an inch, this end moves a 32nd part of an inch. Also, there's another way to see it. We can say if this wiggles an inch, this wiggles half an inch, this wiggles half an inch, this wiggles 1/4 of an inch, this wiggles 1/4, an eighth, this wiggles 1/16, and this wiggles a 32nd of an inch. Now, I'll say a little bit about where these levers are. Occasionally in this world, you have to weigh very heavy things like truck scales. Perhaps you've seen a truck drive onto a scale. And the truck goes onto the scale and they weigh the truck. And you might wonder, gee, how do they weigh such a heavy thing as a truck? And if you were actually, there's a little house there by the side of the road in which there's the weight master is in there. And you might think, gee, that weight master must be moving some heavy weights to weigh that truck. But if you were to look in the window, you'd see the weight master, if he was doing anything, he moves some very small weights. How is he able to balance the truck with some very small weights? He has what there is under the ground there, hidden beneath the ground, is a compound lever. And that's what enables a very small weight to balance a very big weight. It also, when you notice that when the truck drives onto the scale, you might think if a truck drove on an ordinary scale like they have in a grocery store, once the heavy weight was on the scale would go way, way, way down. But you see, with one of these compound levers, the end with the truck on it only goes down 1/32nd as much as this end over here. In other words, there is only a very tiny movement on the end with the truck. These truck scales, of course, are based on railroad scales, which we used to weigh locomotives and railroad cars. And recently I saw an old railroad scale in San Francisco. They abandoned the Mission Bay Railroad yards, and there, in the process of abandoning it, they tore off the top, and you could see this beautiful mechanism beneath the ground of lever after lever after lever, made out of steel, very fine jewel-like bearings where they pivoted, made out of very hard steel, for actually weighing railroad cars. And I thought, what a beautiful thing is being thrown away. Here's a real museum piece that should be saved, but people don't appreciate mechanical things. They don't appreciate really beautiful mechanical things. And so the whole beautiful mechanism was buried by a bulldozer. They just shoved dirt into the pit that had the railroad scale in it. I thought, gee, we don't really appreciate our own art, do we? Well, anyway, so much for the railroad scales and so much for this. I'd like to tell you one more moral about it. Years ago, the school where I teach got a little programmable computer. It was one of those little pocket computers that was programmable. And naturally, I took it home as soon as I could, and I tried to learn a program. And I did learn how to program it, and I wrote a little program that would add 1 + 1 + 1 by itself, and the numbers would appear on the illuminated there where you read the numbers out. And so it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I was so proud of myself after I got it started running. It was late at night, around midnight. I went to bed. And I woke up early the next morning, and I went back out to the kitchen where I had played with the thing the previous night. The thing had been running all night long, and I looked at it, and there it was still adding. You know, it was maybe up to a couple 100,000, 100,001, 100,002, 100,003, 100,004, and the thing was running on. And so that was it. That was like this scale. The bottom one, each time 1 × time, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8. It was just each time you add a little length on the bottom when you add one more number, and it adds up. The next night, which I guess that was Friday night, I guess Saturday night I was also home with nothing to do. And I took out the computer again. And that night I learned not how to add, but I learned how to make it multiply by 2 times 2 times 2. So go 2, 4, 8, 16. And the numbers would appear on the dial each time. And it was self-programmed to multiply by itself. And I set it out and I watched it for a while. And then I decided I had to go and brush my teeth because I was getting ready to go to bed. And after I brushed my teeth, I came back into the kitchen to look at the thing one more time in the dark at the luminous dial running. And the thing had already saturated. It had filled up the dial completely and it wasn't running anymore. It turns out that multiplying by 2 makes you grow geometrically, and you grow enormously fast, and it fills up the thing. Doubling and doubling and doubling is much more effective than just adding. And that's what the trick of the compound lever is that instead of adding, it multiplies, and that's why the force gets up and is able to beat the ordinary lever. Just taking a machine and making it bigger, sometimes if you hook a thing like that together and use a little imagination, you can make it become a lot more powerful, a lot quicker. Okay, now I want to pose another problem, and here let me draw a picture and show it to you. Now I'm going to have two things here, and here are the two things that I'm going to have. One. And here's the first thing. There it is. Hope I draw this right. What have I drawn here? Well, I've tried to draw a pair of pliers. And this pliers, let's look at it. This is the pivot point, and there's a certain distance out to these are the working jaws of the plier. Maybe they're serrated so they could grab something. Okay. And here's the handle, and it's twice as far back. You're going to grab it at the very end. And now I'm going to draw another machine, and here's the other machine that I'm going to draw. And again, I'm going to try to make it 1, 2, 3. I'm going to try to draw it rather carefully. And here's the machine right here, and there's the pivot back here, and then it comes up like this. Part of it does, at any rate. And there's some jaws there. And there'll be jaws here. And then I'll make it come on like this. And make this part come on like this. And what have I drawn here? You've seen this thing too. What is this second thing that I've drawn? It is a nutcracker. Now it turns out that you would put a nut in like this, and of course this would be your nut, kind of a flat nut, and you'd crack it. But you don't have to crack a nut with a nutcracker. You could also crack a nut if you wanted to with a pair of pliers. You could put that same nut in here. What kind of a nut does that look? More like an almond than a walnut. Okay. Now, again, both of these things, remember, the nut is 1 inch from the pivot, and the place where you put your hand out here, where you grip it, it's 2 inches from the pivot. And again, here we have the same configuration, 1 inch, and out here it's 2 inches out to here. Which of these two tools would be more effective for cracking the nut? Why don't you think about it? Which is going to be more effective? In both cases, your grip is equally strong. In one case, you grip the nutcracker. In the other case, you grip the pliers. Which is going to exert more force on the walnut?